I'm really excited to speak to you guys tonight about what we've been doing on Mars. So you guys are coming from a geology background, and so this is kind of a great way to tie in what we're doing on Mars with what we've seen on Earth. Everything that we study on Mars, we're kind of basing it on our understanding of Earth. But I think that now with the information and the level of information that we're getting back from Mars, we can start to tie it back and understand Earth a little bit differently because of what we've seen on Mars. And so I'd like to encourage you as geologists, as we go through this, to think about how you would approach this Mars system and how this could make you think differently about the work that you've been doing on Earth. We've been curious about Mars for a long time. Probably the ancient Egyptians were some of the first that we know looked out in the night sky at Mars and wondered if there might be civilization there. Through the 1800s, when we started getting telescopes, we kind of mapped out the surface of Mars and thought there might be societies there. There might be these long channels running across the planet. Early astronomers said it was covered in canals. Those turned out to be kind of figments of their astronomy, their telescopes. But since we've gotten better imagery of Mars, we're still thinking that there are times when Mars could be something that would really tell us more about Earth. And so while that may not be the present day, maybe about 4 billion years ago, the planets could have looked a lot more similar. I'm going to throw in some caveats here early on because these questions come up frequently. There are some differences, and actually, faint young sun is not actually a difference, but when we're thinking about early Mars, and we're thinking about a planet that could have been similar to early Earth, we need to remember that 4 billion years ago, the Earth was only 75% as bright as it is today. We need to remember that Mars does not have a magnetic field. It may have very early for 100, 200 million years, but it definitely did not retain that magnetic field in the same way as Earth did. Because of that, the atmosphere has been stripped away, and it has a very thin atmosphere, and that likely happened very early in Mars history. It does not have plate tectonics, never developed those. There's not significant influence from organics. We can definitely say that. And of course, it has lower gravity. With these caveats in mind, there's still actually an interesting amount that we can compare between Earth and Mars. And really, once we realized all these caveats and got some of our first images of Mars, I think we were actually pretty hesitant to think that Mars would teach us anything. And so it took us a while after getting the first images to come to find a way that we could really use Mars to compare back with Earth. One of the things that kind of benefits it, despite those caveats that I mentioned, is that 75% of Mars' surface preserves a time from before 3 billion years ago. And so that's a time on Earth that we don't have very good records of. As you know, we've got rocks up until almost 4 billion years ago and a few minerals that tell us about the time before that. But on Mars, a lot of the surface preserves that time period that we don't understand as well on early Earth. And so this is part of what gives us an advantage. Mars has a surface that we can clearly investigate what kind of processes were happening in this time more than 3 billion years ago on a planet fairly similar to Earth, at a time when both planets had slightly different radiation environments. Neither of them may have had plate tectonics at that point. And yet still there were a lot of important geological transitions happening. Especially on Earth, we think that might be the start of when life started to exist. On Mars, we're not as sure about that, but we do know that there were several major transitions that occurred on Mars in that time period. Early on, there were more clays. Later on, there were more salts. And since about 3 billion years, we've really had mostly dry, windy Mars. What does this look like in pictures of the actual surface? Well, these were some of the first pictures that we returned. So we had mariner missions in the 1960s, but in the late 1970s was when we really got a complete picture of what Mars' surface looked like. And it is mostly barren and moon-like if you look at it on a larger scale. But there are several places that show us that it was more geologically active in the past. In particular, of course, we're interested in flowing water. And so we see a number of different channels at different scales that show us that there were river networks at some point. There were flood channels early on. in several different kind of morphologies and locations across Mars. So we know it was more geologically active, and we know that flooding type processes or erosive processes were happening. We also know that in the end of a river channel, you're going to find the deposits from that river. However, unfortunately on Mars, without plate tectonics, we actually weren't sure for several decades if there would be any place where we would really be able to investigate layered sedimentary deposits at the end of one of these channels. If they're all buried, it's hard to drill, as you know, and especially to bring that kind of technology over to Mars would be very difficult. And so we had one advantage, which is that there are craters, which are nature's drills for us. So if we go over to a crater, it's exposed a lot of subsurface terrain. However, to really get a good spot with different layers, we were hoping there would be something else that would help evacuate those sedimentary deposits. And it was actually in the early 2000s when we started to find real evidence of those type of locations on Mars. So this is after some of our surface missions as we're kind of progressing towards finding better and better landing sites. This is one that we noticed early on and has been kind of suggested as a landing site many times and never chosen. This is a big crater system that we know that water flowed through. And we know the water filled up several of these craters and breached the rims. And it came over, in this case, over to the smaller crater. And I'm going to zoom in on this box right here. Within this crater, we can see the delta deposit from the river that flowed into this crater. Now, interestingly, the lobes of the delta are exposed as high surfaces here, and the terrain around it, where we would have had more of the mudstone or finer sediments, has eroded away. And so we actually have had wind that has eroded out this delta into an inverted deposit. And because of that, you could, in theory, with a rover, drive around and see the different layers of deposition within the crater. And so there are opportunities on Mars where we'll be able to investigate those sedimentary deposits at the end of the river systems if we can find places where the wind has been blowing sediment away as opposed to depositing it. So we looked all around Mars. We looked in all of the places where craters had opened up stratigraphy or where the wind had opened up stratigraphy. And we looked at the minerals that we could see using a spectrometer from orbit. This is the Mars Reconnaissance Orbiter, and the CRISM instrument is a spectrometer. So we use that to detect different mineral types as we look at all of these different layered deposits. This is an example of one of the layered deposits that I'll talk about more. But as we looked at different layered deposits, we made stratigraphic columns for each of the deposits. And these are just color-coded. Sorry, there's a lot of words on here. The color code is that green is phyllosilicate deposits, phyllosilicate minerals. Yellow are sulfate salts. Interestingly, Mars has very few carbonates, just a few carbonates, but quite a lot of layered sulfates. And then this brown is the layered dust that is still blowing around on Mars today. So what we want to capture are kind of what caused some of these major changes in Mars climate history. And if we look at these just in general, where we found layered deposits on Mars, there's only one where we actually capture all three of those major types of deposits, where we go from those phyllosilicate minerals to a large deposit of sulfate salts to the dry, dusty terrain. And that's Gale Crater. And that's why we selected Gale Crater for Curiosity. Now, Gale Crater is particularly interesting. It is a crater, and that could have been the reason why these deposits were exposed. But instead, I'm going to zoom in on the crater here, the deposits are exposed on a mountain in the center of the crater. So when this crater formed, it's about 155 kilometers across, or 110 miles across. And the impact was large enough to cause a rebound in the rock itself. So if you see kind of a slow motion water drop and you imagine that rebound, we have a central peak of the crater which creates this kind of pointy knot right here in the middle of the crater. And what appears to have happened is that much of this crater filled up with sedimentary deposits through time and likely was kind of more of a flat surface, maybe preserving that central peak. And then the wind came, and the wind actually chose to undo that deposition and blow the material out of the crater. There is actually wind acting today, which helps us see part of what that process might have been like, although it's sort of foreign for our understanding on Earth. this dark sand is being blown today. The wind is coming from this direction, the dark sand blows around here, and you might be able to just see a little bit of that dark sand actually escaping out of the crater. So it appears that this type of sand-based, wind-based removal of rock actually eroded basically a moat around the central peak. And in doing so, it left some of the sediments that were pressed around this peak in this mountain and exposed them beautifully along the side. So we have taken advantage of this as our landing site for the Curiosity Rover. So because we have this set of deposits that are now accessible today and layered, and again, those are the deposits that best preserve that whole series of changes on Mars, from a time when phyllosilicates were deposited to sulfates to dry, windy, iron oxide-rich dust. So this spot right here is our landing ellipse where we plan to land the Curiosity Rover. That's the center of it. This is 99% chance of landing in this zone. So we landed just a little tiny bit kind of downwind from the center dot, but actually very close to the center. And we landed with this robot. And the Curiosity Rover is the size of a small SUV. It's quite large. It's about 2 meters tall. We have a variety of instruments. We have 11 different instruments, and I know that's a lot of acronyms. We have several things that we're able to use daily. So we drive around, we take pictures, we monitor the weather and the radiation environment. We shoot a laser from this eye at the top of the rover. That laser can shoot up to 7 meters away, and it will turn a little tiny bit of rock into a plasma. And then we have a spectrometer that will measure that plasma to get the composition of the rock. This is probably our most, exciting looking instrument. And we do get to use that one every day. So we do actually get to choose what we want to shoot with a laser on Mars on a daily basis. On a few times a week, or on a sort of more rare basis, we're able to fold out this robotic arm. The robotic arm is just over 2 meters tall, so it can reach kind of quite a range of rock right in front of the rover. And if we're able to set that down, we can get really good, we can get kind of a chemistry measurement of a spot about the size of a penny. And we can take higher resolution imaging with a camera right on the end of the arm, held very close to the rock. On really rare occasion, and we're talking about, say, 15, I guess we have between 15 and 20 measurements. We're able to either drill into the rock or scoop up some sand. And when we do that, we have high resolution instruments on board. So we have a mass spec and an X-ray diffraction instrument on board the rover, so we can do those analyses on Mars periodically. They do take us a very long time to complete on Mars, and so because of that, it's quite rare. So the first challenge was really not up to the geologists, and so that was getting this robot to Mars and to Gale crater. And so I just want to show a quick clip of what that was like. And certainly the engineers had to design a way to land a car-sized robot on Mars. And when it was landing, it was 14 light minutes away from Earth. It takes 7 minutes to get from the top of the Mars atmosphere to the surface of Mars. So you can probably quickly do that math to say we couldn't control it at all. And so this all had to be pre-programmed. And we called our time of receiving the information to 7 minutes of terror. But I just want to show you a kind of shortened clip of what that. I'll strongly encourage you to go home and watch this, because it was truly an inspiring night. And I think one of the really cool things about working with Mars Exploration are the number of people around the world, and through these engineers that are really able to come together and celebrate these kind of accomplishments. And truly, as a geologist, I'm purely benefiting from the amazing technology that the engineers have designed and put together so that we could get this kind of robot to Mars. We always say that they're able to kind of, after it lands, they hand over the keys to the geologists. But of course, we couldn't do any of this without the amazing technology that they've built and put together.
Can you get to Jim Tucker and he'll have the office put it on the talk, the URL
Yes.
link for that?
Yes, absolutely. Absolutely. And one of the, I guess the highlight from this video is just that it goes around the world and shows different groups around the country and around the world that we're celebrating as we landed. And so it really does bring people together. And I'll show, actually I've got a couple of kind of snapshots. These are from the video that highlight some of the impressive engineering. And one of those is this shot. So we have, well, at the time when Curiosity landed, we had 2 active NASA satellites that were orbiting Mars, and 1 European Space Agency satellite. One of the NASA satellites was working to immediately communicate. As the rover was landing, it was sending signals about its status, and as each step checked off, to the orbiter, which was immediately relaying those back to Earth. So one of them was completely used for relay, and the other one was programmed to fly just over as Curiosity was landing. And during that 7-minute sequence, there was about a minute and a half when Curiosity was suspended from the largest supersonic parachute we've ever built. And that orbiter, Mars Reconnaissance Laboratory, managed to capture this picture. So this is a real image of Curiosity dangling from that parachute as it's landing on Mars. And just the coordination of that alone is truly amazing. And the fact that we kind of get this picture at the end of seeing those 7 minutes is amazing. Furthermore, okay, so as it was landing, I don't know how many of you have kind of seen parts of this landing sequence. The first part is that it hits the atmosphere and has a heat shield. That heat shield drops off and releases the parachute. The parachute gets it slowed down, but because there's not that much atmosphere on Mars, the parachute can't do all the work. And so the final step is called a sky crane. And that's this descent lander. So this descent piece drops the rover from some cables and uses these jets to slow it down and kind of position it over a clean spot on the ground. It's checking for a clean spot, positions it right over a clean spot, and sets the rover down, and then cuts these cables, and this flies away and crashes. Yeah, we all thought they were crazy when they said this. It worked perfectly. So we actually had a camera on the bottom of the rover during this experiment, that's what it felt like. So as this was landing, these jets were blowing out to slow it down. And this was the picture that was taken from the bottom of the rover as it was landing. And you'll see that the blast of dust from the surface on one side is actually a lot bigger than on the other side. And the reason for that is because there was a little bit of wind on Mars that day, and this was prepared to accommodate for that by cutting the horizontal velocity by tilting just a little bit, and so the blast is much larger on one side, so that it was properly cutting that velocity and depositing the rover safely on the ground. Remarkably, this all worked completely perfectly, and so they did hand over the keys to the geologists. And we got to take pictures of Mount Sharp from the ground. We'd always been using those kind of orbital pictures. We'd had black and white imagery, 25 centimeters per pixel, which is really great. But when you can see it from the ground in true color, just the way this is adjusted, it's white balance so that the sky is blue. It wouldn't really be blue on Mars, but since that's the way we see things on Earth, it helps us. So this is the true color imagery of Mount Sharp, and this is a beautiful panorama. I've zoomed in on a part so you can see it. And we can see the layers that we were so excited to explore, right? So here's the dark sand dunes that are the current active sand blowing around Mount Sharp. The layers of phyllosilicate clays are right down here. These kind of ridge-forming units are the sulfate ridge layers, and the dry iron oxide dust kind of forms a set of really particularly large planiform-looking features near the top. There's an unconformity between the sulfates and that dry iron oxides. Now realistically, I'll be honest, we're not going to get to this boundary. We're currently right around this phyllosilicate to sulfate boundary. And I wanted to point out one other thing. So the other thing is that this is actually 5 kilometers tall. So we get a lot of foreshortening in our images. With the lack of atmosphere, if something's really far, you can still frequently see it very clearly. And so this is actually a very, very tall mountain preserved in a crater by the wind. So once we landed, we got these images. We've all been waiting to drive over to Mount Sharp for, 5 or so years since we actually selected the landing sites pretty late, but a lot of people had been hoping for this one. This is our glass zone. So this is an image, again, taken, same satellite that took the picture with Curiosity from the parachute. This is where the dust was removed as Curiosity was landing. And this is the way towards Mount Sharp. We have between 400 and 500 scientists at any given point on the science team. So you have been on road trips before, and you can try to imagine having one car and about 400 drivers. I think the only decision we have ever actually made that was basically unanimous was to drive in the wrong direction when we landed. This is the way we drove. Actually, if you can see closely, these arrows are following the trace of the rover tracks, because again, this is a real image where Curiosity is this bright pixel right here. And the main reason that we drove this direction was that we were only about 500 meters away from the lowest point in the northern half of the crater. So the lowest point that we could start at. If you're going to put together the stratigraphy, it's nice to start at the base and work your way up. And so we wanted to start in that lowest layer, especially, water flows downhill. We had all sorts of different reasons. But we drove right over there to get started. On our way, we already were pretty excited. This is the first time that we could find a conglomerate on Mars. None of our previous landing sites had led us this quickly to water-lane surface deposits. We had kind of one deposit that we previously observed that was a sedimentary rock, and it was dry Aeolian dunes. So these conglomerates, which actually this rock exposure got exposed by that dust blowing away at the base by those jets in the landing sequence. And so it was basically the first rocks we saw were conglomerates. You can see some pebbles in here that are up to about 1 centimeter across. So this river that would have carried the rocks here would have been knee to waist deep. And so we were really excited. Okay, we're heading in the right direction. We're in the right spot. Water is flowing here. We kept going. We kept seeing more indicators of fluvial cross-stratification. We drove through a lot of sandstones, conglomerates, and we stepped down into that light tone layer that we said was the lowest layer in that side of Gale crater. And we actually stepped off of the sandstone ledge and down into a soft mudstone. We get to name things on Mars. This was the Sheepbed mudstone. We were naming things after units in Canada at that point. So we stepped down into the Sheepbed mudstone. As soon as we looked around, we started seeing just interesting diagenetic indicators that we were, in fact, in a mudstone that was probably deposited underwater. One of these were cineresis cracks, which had been filled with some cement that caused them to be erosion resistant, so that we can see kind of the three-dimensional nature of these cracks. Cineresis cracks are similar to desiccation cracks. It's when clays kind of shrink, but it's when that occurs subaqueously as opposed to in the sediment-air interface. These form underneath the sediment-water interface. They're rarely preserved on Earth except in the kind of Neoproterozoic or earlier because of burrowing organisms. So this just highlights a first order, start to think about things a little bit differently if you don't have organisms to disturb the soil. We decided that this was a spot worthy of our first drill hole on Mars, and this was the robotic arm actually deployed and drilling at our John Klein target. You can see our goal, Mount Sharp, in the background. We were very excited. When we drilled, this was just the color of the drill hole, right? The color of the rock. Everything we ever see on Mars is red. Like, we stretch the images all the time to try to get just a little more color variation in what we see. But what we realized as soon as we drilled was that we didn't actually need to stretch this. This was a gray rock underneath. And so just to give you a sense, this is the drill bit. This is about a centimeter across. This is the scoop with the sample that was collected as we drilled. We're only able to drill about 5 to 7 centimeters, but that's sufficient to kind of collect sample within the drilled bit and deliver it kind of within our internal system. So we send in the scoop. And then we're able to deliver that to our XRD and mass spec. And so we were able to confirm with the XRD and mass spec what we had suspected from the nature of the rock. This is our trace from our XRD. So instead of having a receiver that moves, we actually have a we move the sample and reflect X-ray beams across the sample as it's being kind of rotated by a piezoelectric shaker. And as we rotate the sample that way, it causes the X-ray reflections to go kind of in this circle across our CCD. So we integrate over the circle, and we're able to get a typical X-ray pattern. But the circles are prettier. So what we see here, this is a very typical, this is a sand on Mars that we had scooped up before we got here, where we saw kind of a typical basaltic sand for Mars. When we scooped up this mudstone, or when we drilled into the mudstone, we got a high reflection in these low angle reflectors, and so that's indicative of phyllosilicate minerals. And in fact, this spectrum showed us that this was probably about 20 to 30% phyllosilicate minerals, clays, definitely mudstone. When we heat that up with our mass spec and we're able to measure the evolved volatile species that come off of it as we raise the temperature, we can see that it had multiple forms of sulfur. The water was also consistent with phyllosilicate mineral. It had multiple forms, we had multiple forms of iron. So we had a redox environment where microbes would have been able to exploit these redox differences in iron and sulfur as they existed. And we had an environment that appears to have been a pretty freshwater lake. It wasn't terribly salty. It wasn't terribly low pH. We're not seeing like jarosite in this sample. Previous samples on Mars had all been kind of more like battery acid. So this was really exciting to find a freshwater lake that would have had that those redox differences to supply some kind of chemolithotrope with the energy it needed to survive if we'd had microbes here. We were also able to look for microbes or look for organics, and we found a few very small organic molecules. We drilled in 2 spots very close to each other. One of the spots had more of these organic molecules than the other, so they were pretty variable across the surface. But also, we're talking about chlorobenzene, which can also be delivered by cometary impact. So we do expect some level of that kind of organic at the surface, regardless of the actual evolution of life. However, to be able to say that we had a mudstone, that we had a lake sitting on the surface of Mars that would have been habitable for Earth-like life was really a revolutionary statement in our understanding of Mars, and something we had really sought with this landing site. And so our decision to drive in the wrong direction was vindicated when we caught onto this. And I'll just highlight one other finding we had at this site. I noted that we stepped off of an erosion-resistant sandstone ledge to go down into that mudstone layer. That was our drill hole. We had 2 drill holes. One of them was closer to the ridge. When we heated them up with the mass spec, we were able to get an argon measurement. And in the composition of the material that we dropped out of the scoop and we used the arm to kind of measure, we were able to get a compositional measurement which included potassium. And so through a little bit of trickery, we got the first age date on Mars. The potassium argon age of the sediments in this lake were about 4.2 plus or minus 0.3 billion years old. This was very consistent with our understanding of the system. So the crater itself is more like 3.6 to 3.8 billion years old, but the rocks around it are very old, are Noachian. And so they're from this era about more than 4 billion years ago. So this actually was consistent with counting craters on the surface to estimate its age, so this was very exciting to us. Interestingly, we also did a cosmogenic exposure age using helium and neon, and actually that was very young. So 80 million years, plus or minus 30 million years on Mars is younger than we expected significant activity in these kind of sediments. And it seems that this erosion-resistant ledge is actually kind of currently eroding, that there is active erosion continuing in this crater on Mars. And that's really exciting for us because that definitely increases our chances of being able to find any preserved organics, which sitting on the surface of Mars will be constantly irradiated. But from this, we learned that if we try to aim our samples for something just below a retreating ledge, we might have a higher chance of finding some kind of organics. So we were pretty excited to get that. Okay, so then we said, okay, we have that beginning of the story. We have the first layer. We are in a good place. It was a kind of habitable lake. Now let's book it towards those layers that we've been admiring for several years now. Pass over those sands and get up to the layers on the mountain.
Quick question, the dark sands that blow around are mostly iron oxide, or?
It's a full variety of basaltic minerals. So there's olivine, pyroxene, there's some plagioclase, there's not very much quartz. There are lithic pieces in there. So we started booking it. For us, booking it is going 2 miles a year, I think. So unfortunately, even at that crazy rate, we managed to do some damage to our wheels. So when you look down and you happen to take a picture of the spacecraft and you realize that you can see Mars through parts of it, it's not a good sign. So we stopped and reevaluated. Whenever this happens, whenever we run into a problem on Mars, of course you can't take the car to a mechanic, so you just have to figure out what the best way to work around problems like that are. And so we studied kind of extensively how the wheels might break down and what kind of things we could do to minimize the damage and how long they would last. And so because of this, we quickly changed our driving style. One other thing that I like to note in this picture is just that the wheel itself has some holes in it. These ones are intentional. And these are kind of just a different pattern so that if you're looking back at the tracks, you can see how many times the wheel has, it's just a very quick double check of how far you've actually traversed. Originally, the Jet Propulsion Lab was designing the wheels, and they put JPL for the different layer. So you get these zigzags and then JPL written across Mars. And NASA caught wind of this before launch and said, you can't brand Mars. So they said, fine, and they put these holes in it. As soon as it launched, they did a press release and said it's actually JPL in Morse code. I think now that these are the pictures of the wheels that we're sharing, they might have second thoughts about that, but that's what it says as we drive around Mars. Again, this is what happens when you have 400 people driving one robot, or 5 experts. You have about 7 different paths of what's the safest way to traverse without hurting the wheels. Certainly, working on these missions requires a lot of compromise in both, which direction you drive, longer term, and day to day, which rock you shoot with the laser, and why, how you spend your time. But it tends to work out well. We ended up taking, you may be able to see it, there's a light pink path that traverses around here that kind of goes through softer areas. We're afraid of getting stuck in sand, and we're afraid of driving on sharp rocks, and so you have to kind of cut the balance carefully. This one cuts through a few gullies, but ends up with beautiful views within those gullies of the sedimentary rocks on either side. And these were just a couple of those views as we traverse. And we love taking that chance. We've got that 2.5 meter robotic arm, which we can stick out, and it does have a camera on the end. And so because of that, whenever we stay at a spot for a long time, usually to drill into the Mars rocks, we'll pause and use that arm to take I think it takes about 80 images minimum of rotating the arm in kind of all sorts of directions that it wasn't necessarily intended to be rotated in order to take a selfie on Mars and show the world that we are in fact looking at the rocks. But these actually are just some of the images that kind of capture us the most, because we get to see these instruments and this robot that we built as humans, and have those actually sitting on the surface of Mars, right? This thought of the robot actually exploring always brings joy to us. And you can usually tell if you're talking to someone on the team, it takes, I think it's almost always less than 10 minutes before we start acting out parts of the rover because we all kind of relate to this robot that's exploring for us, even though we don't get to go to our field site. So these are some of the layered rocks that we were exposed to. A lot of them are fluvial sandstones. And so we keep driving. These are some of the fluvial sandstones that really started to help us get a stratigraphic framework for this system. All of these are kind of pebbly sandstones, and each of them are dipping. So this is going towards the mountain. Each of these are dipping down towards the mountain. And so every layer we kept seeing these kind of stratified units, and all of them were dipping towards the mountain. And as we got closer, more and more of them were dipping towards the mountain. And I'll show you our stratigraphic interpretation. But as soon as we got back here, just before we got to the dark sand, we got right back here, and we stepped down again from a ledge into a mudstone. So we had another one of these. You step down, you get to a mudstone. This one was a very evenly laminated mudstone. The laminations vary from a millimeter to a couple of centimeters. This is one of the thicker laminated sections. But this laminated mudstone actually continues for an extraordinarily long time and is quite steady as we've been climbing up the mountain. So I'll talk about that. But just to put this in our stratigraphic framework, here's an image. This is an overhead map of our traverse. So this is where we landed, and this white line is showing you where we drove. So we pretty much did, except for that little jog over to the Sheepbed mudstone, we pretty much booked it straight up to the layers of interest on the mound. This is actually from about the first 3.5 years of the mission, but this is the most interesting section for this. The dots are where we stopped to take a chemistry measurement. So those are places we pulled out the arm and took a chemistry measurement. And the color code is to show you the elevation. So we were actually gaining elevation from the beginning. We sort of arbitrarily delineated that the mountain started, not arbitrarily, but there was that ledge which cut down from the sandstone to the mudstone, which we delineated as the base of the mountain. But our whole traverse was really going up towards it. This is our distance traveled on Mars, this is our day on Mars. A sol is one Mars day. But it's a proxy for the distance we've traveled on Mars. And this is elevation, which we use as a proxy for stratigraphic time. We've been using elevation because it's the easiest. We're just now getting to some layers that may or may not be tilted, in which case we really have to reevaluate that. But for this section, it seems to be pretty true, that the layers are pretty flat. And so just to put that framework on it, we are looking at kind of fluvial deltaic deposits just as we're entering a lake. And interestingly, those seem to be prograding. And so those kind of layers that I showed you of pebbly sandstones dipping down towards the mountain are probably prograding deltaic lobes before we're entering the lake. And so for much of the traverse, we believe we were kind of at the edge of, we were sometimes seeing conglomerates, frequently seeing pebbly sandstones or sandstones, sometimes fine sandstones, probably just kind of traversing along the edge of what would have been a transition between those fluvial deposit, a fluvial deltaic transition point. So much of our traverse was through that at the first year or two of the mission. And let's see, yeah, there's the conglomerates and pebbly sandstones and the outcrops that we were looking at as we kind of traversed along that pink path that let us see some really nice outcrops on the side. Then we get to the Murray Formation, and that's that laminated mudstone. And again, some of it was very thickly laminated, and some of it was very finely laminated, but it's really consistently laminated, and we've been able to climb up through several units of that, several parts of that. We have seen a couple, this is a simplified picture obviously, we've seen a couple of fluvial deposits that just kind of broke through parts of the Murray Formation. It does seem like it's still a prograding environment, which is interesting. After both of these groups were deposited, we found an unconformity. That unconformity kind of traces the shape of the mound as it is today. And so if this whole mountain was exposed by wind that chose to evacuate out the deposits that filled that crater, it's not the first time in history that that happened. It looks like that happened at least twice. So above that first unconformity, we see wind-blown sandstones that sit as buttes on top of the mudstone. So we'll have laminated mudstone like here, capped with this beautiful cross-laminated Eolian basaltic sandstone. And here's an image showing you those kind of meter scale cross-stratification, dune cross-stratification. And so we've been able to actually, because of this, we've encountered a variety of different units that we're able to learn from. And so I'll go into a little bit of a story of kind of something that we've learned from each of these three types of environments. Starting with those fluvial deltaic rocks. So again, this is when we were starting to investigate the sandstones. And this is one of the main projects I was working on for my PhD. But we were looking at these fluvial deltaic rocks and wondering how much we could separate the different compositional influences on those rocks. We know they're coming from basaltic source rocks. They're sorted by transport into the crater, and then they're cemented. There's, in the case of the fluvial deltaic rocks, they're not too affected by lake water chemistry, but there's certainly groundwater chemistry and diagenesis that has cemented these into rocks. And as we tried to kind of figure out what was going on with these, because there was a wide range of compositions. And so there were kind of initial thoughts that maybe we had a real variety of source rocks. Maybe we've seen a lot more evolved, we're seeing a lot more evolved volcanic rocks on Mars and different kind of igneous evolution models. We're starting to go forward when we pulled them apart and said, hold on, let's look at these more closely. So first off, you know, optimally, if you were looking at a basaltic sandstone and trying to understand, you know, what's the composition that's coming in from the grains and what's the composition that's coming in from the cement, you would cut a thin section, and that would be absolutely amazing. We would love to do that. Instead, we get the composition of about a penny-sized spot, which is influenced by the dust sitting on the surface, and of course represents a combination of all of the different mineral grains in that area. And we only get to get this even you know, every few days or a few times a week. And so we're working with, you know, less data than we'd like to for this question. But because we did get over 100 of these analyses in that fluvial deltaic unit, we were able to kind of sort them out just based on the characteristics of the sample. And so we just started out by sorting them by grain size. So when we sorted them by the grain size of the sample, we realized that that was actually describing a lot of the changes in the chemistry. So I've just shown one example here, but you go from the coarsest rocks to the finest rocks. In aluminum, the coarsest rocks are enriched in aluminum relative to the finest rocks. And so the coarse grain rocks, it's not just aluminum, they're also enriched in sodium and silica. The finer grain rocks were enriched in kind of all of the mafic components, iron, manganese, magnesium, titanium, chromium. And so we realized there's a significant sorting effect happening in these deposits. And that may be able to explain more than the idea. It's a little more comforting than trying to say that there were really evolved volcanic, you know, you don't want to say there's a granite on Mars on the basis of a pile of plagioclase that happened to get sorted out. And so one of the ways we double-checked this was to model each of the compositions that we had as to kind of pick a composition for plagioclase, pick a composition for pyroxene, pick a composition for olivine, and see if when you take the composition of the rocks that we saw, if you can make that composition with a combination of these primary igneous minerals. It turns out 90% of the rocks that we saw could just be combinations of the same set of igneous minerals sorted slightly differently. And so you really can, this is almost magic that this worked out, right? But that in fact we could explain all of these compositions, and it was just that the coarsest grain fraction of the rocks had a much more significant plagioclase and potassium feldspar component. Like 60% of the rock would be plagioclase and potassium feldspar, whereas the finest grain rocks would be the opposite, 60 or 70% olivine and pyroxene. So we kind of looked around for some kind of confirmation, and we found that the one rock that we saw that was the most promisingly, like clearly igneous looking rock was in fact an aluminum-rich basalt with large plagioclase phenocrysts in a basaltic ground mass. And so interestingly, you could just take this type of basalt, and if you spread that out, and broke it up and brought just the minerals down into the crater, you would end up with the compositional spread that we saw. That's kind of weird. I think if we broke up rocks on Earth, we would generally expect there to be some more weathering. So first order, this system seems to be pretty cold, or it's not conducive to open system weathering. And it's kind of interesting that we managed to cement these rocks without actually changing those initial mineral components. And so there's obviously some sway in there, and there could be just a little bit of open system weathering, but it's pretty negligible when we look at the compositions. So this means that transport sorting is one of the dominant effects that created the compositions that we saw. Now I'll note, this is mostly aluminum-rich basalt. There were a couple of patches as we were driving through. There was one patch that was almost 20% potassium sanidine grains. And that was one where we actually got a mineralogy assessment, or got a mineralogy sample, so we know, okay, something was going on there because we have a lot of this kind of potassic mineral that doesn't fit with this picture. And it's really only in one spot. And so we've got a couple more things to tease out in this picture. But interestingly, for the majority of the rocks in that fluvial deltaic group, there was very little weathering, it was probably very cold, and you broke up an aluminum-rich basalt with plagioclase phenocryst. Or it's consistent with that story. Now let's look at the windblown sands. So we noted that we've got a couple of different types of windblown sand that we've observed. We have the active dark sand that's blowing around today, and we have that preserved unit above the unconformity. And so to start with the active sand, interestingly, when you look at a dune on Mars, it looks like this. Probably most of you have seen a sand dune on Earth, and you're used to a picture more like this, where you get to see, and this isn't high resolution enough, but there are a few centimeter scale, or 5 centimeter scale ripple bedforms, and then there are the meter scale, people walking along the top, tens of meters scale dune bedforms. On Mars, we see this other wavelength of Aeolian bedform. And these bedforms are about a meter, meter and a half across, and they're sinuous crested. So these may look more to you like subaqueous ripples that you typically see on Earth. This wasn't fully expected. I think we sort of thought maybe Mars had just larger ripples based on either gravity or atmospheric density, but it turns out it still has the small ripples, the small few centimeter scale. It just also has kind of a third wavelength of bedform.
This is subaqueous. This is subaqueous, you mean?
No, this is active Aeolian.
Active Eolian. Okay.
Yeah, it just looks like subaqueous. I definitely agree. So this is active Aeolian. We actually saw the small ripples moving. And Planetary et al. Called these large ripples. So we've just kind of recently found these, recently established them. And they showed that, in fact, mechanistically, we still don't really understand how these form. But kind of in an explanation of how they fit in with our Earth ripples, the low density of the atmosphere causes a different viscous boundary layer at the surface. And so you actually do form these longer ripples just like you would form subaqueous ripples on Earth. You still form Aeolian ripples by the typical kind of saltation-based process, but you also form these. Now, the second part of that I think is really cool, the second paper that they published, was extrapolating this. And so they said, okay, if we go into geomorphology, we use a lot of these non-dimensional numbers to explain the wavelengths that we see. And so we had kind of a few different models for how subaqueous ripples get their wavelength. Now, when you take a system that has an entirely different atmospheric density, an entirely different ripple wavelength, and you add that to the set of ripples that we'd seen on Earth, you can form a line a lot better. And so this actually helps them, and so they're able to kind of establish this non-dimensional number that says how ripple wavelengths are set. And it applies to all of those ripples on Earth and also includes this. And so this is one of those kind of surprise findings from Mars that goes back and helps us constrain our understanding better on Earth. This has also helped because we know that these only form in a low density atmosphere. And we have records of cross stratification on Mars that we have used to say before that things were probably subaqueous because we have these sinuous crested ripples, even though they're a little bit big. Well, it turns out now we understand a little bit better. We have to revise that and say, okay, there are different bed forms that you could form on Mars, and it's not because the gravity is different. We had already modeled that idea. It's because that atmospheric density is so low. And so yeah, this is an example of that, just coming back to Earth and changing our view.
Can we get the wind speeds from this anyway?
The wind speeds, well, I don't get the wind speeds from that, but we have a wind speed measure on the rover. Thank you. And so we can get winds up to like hurricane force winds on Mars. The number of particles in the atmosphere is much lower. It's a 6 millibar atmosphere. So you may get those moving at, I think it's 60 or 70 miles per hour. But there's not enough particles to really generate change. But that is why we get kind of dust devils and different things on Mars that have helped. Those have helped keep Opportunity alive for so long.
And the planetary dust storm when Mariner 9 arrived.
Yes, and planetary dust storms, which don't occur quite like they did in the Martian, unless you read the book. The second part of the book, they refer to a real dust storm. The first part, it's not going to blow Matt Damon over. I feel the need to clarify that more than I should. Anyway, so there is active wind. We can see it moving sand grains, though. So it is active and it is causing erosion even today. And that's been consistent across different things. The other trick that we're looking into now is that because we have these modern sand dunes and we have the ancient sand dunes, these may be the key to really starting to understand cementation on Mars. So that lithification process is still a bit of a mystery. It seems that throughout Gale crater, cementation occurs without a significant or any significant change in the chemistry of the rocks themselves. We don't have that many carbonates, so there's not carbonate cements, and it can't get buried deep enough and relieved deep enough to produce kind of quartz-type cements. Instead, what we tend to find is that there's about 30% amorphous material in all of our samples, which is great when you bring an XRD to Mars. That 20 or 30% of the sample is X-ray amorphous. And so we're still looking into how that could be potentially helping to cement these rocks. And this is kind of our best chance, I think, to look at these basaltic sands that then got cemented and compare the two.
Kirsten,
Yeah.
is there any possibility that the amorphous material might have been lake muds that simply don't have much reflectance in the XRDs?
So yeah, we try to separate out different components, and I think there's some nanophase iron type components. There's a little bit of amorphous silica, which varies in some of the samples. And you can actually form, I was surprised by this, but you can actually form amorphous salts. And so even something like magnesium sulfate, they've done it in a lab where they took magnesium sulfate and put it under Mars conditions and dehydrated and rehydrated a couple times. And basically it gets stuck between different hydration states. And when it's stuck between different hydration states, it shows up as X-ray amorphous. And so we could be having amorphous sulfate salts, which is frustrating. but I think that's one of the components. So, and there also could be some of the original basaltic glass. So there could be some original components. It just depends on how much that's changed in the last 3.5 billion years. So moving to the last unit, the Mudstone. We've been climbing up through the Mudstone for about 3 years now. One of the most amazing things about this Mudstone is that it is steady and laminated. We've seen a couple of sections with a little bit of cross stratification that either the Mudstone got clumpy or you had a river, the end of a kind of fluvial deltaic system coming in. But in general, we haven't seen real signs of desiccation or evaporation. We've seen exactly one tiny patch of mud cracks. They were about a centimeter across. So there's one little tiny patch that we've seen where it really may have dried up in one spot, but that doesn't even indicate that this whole lake dried up. And this is really significant because we have been driving through these laminated mudstones for 300 meters of elevation at this point. So just as a baseline calculation, that's about 3 million years worth of mudstone deposition in the base of a lake. This plot is again kind of distance traversed or day on, distance on Mars versus elevation. So, you can, if there's any tilting, then of course that number gets changed just a little bit. But on a large scale, we don't see very many indications of that. There may be some up here, and so we're just getting to a part where we need to think about that more. But for the most part, we're looking at a very consistent, long-lived lake system on Mars, and this is again about 3.5 billion years ago. We really didn't think that was something we were going to find. We know the sun was 75% less bright. We know Mars is further from the sun. We know that we're not seeing carbonates in this lake, so we did not have a thick CO2 atmosphere because we should have seen carbonate deposition if that was the case. And it's not crazy acidic or anything like that. We don't actually think there was that much of an atmosphere, probably 1 or 2 bars max, based on a couple other constraints and meteorites that indicate that a lot of the atmosphere was lost already. And so the stability of this lake system in this crater for that long, without desiccation and without any drop stones or indicators of glacial effects here, is really surprising. And definitely, I think, something that will be a long-standing kind of debate after this. And we're going back to the climate modelers. At this point, they're really looking into, what combinations of different gases could create a strong enough greenhouse effect to make this last. We did think that sometimes liquid water existed, but we really thought it would be unstable and based on either volcanic activity or impact activity that could have changed the atmosphere for short bursts of time. And this just seems a lot more steady than most of our models were thinking for 3 million years. We're still climbing up, ongoing mission, and like I told you, we always kind of motivate it with that idea of switching between the clay and the solvate unit, and now we're actually finally just getting to that transition. This is just to show you what it's basically looked like most of the time. It is laminated mudstone. There are calcium sulfate fracture fills running, crisscrossing through the whole unit. Periodically, we see things that look like they could be concretions. We see concretions at different scales. They're kind of patchy. We see different diagenetic features, basically, at different segments. But it just kind of continuously is this laminated mudstone. One of the best ways we have to distinguish between different patches of laminated mudstone is to actually drill into it and get the mineralogy, because we can't separate it out the same way as we did with the fluvial, with the sandstones. So as we were driving, and unfortunately this had to stop, I'll tell you. So there were 15 different drill holes. 3 of them were in that first unit, that fluvial deltaic unit, and really 2 of those were mudstones. So for those of us studying the sandstones, we really only got one shot. But once we got past that, we have 12 more drill holes on Mount Sharp. Again, actually, a couple of those still are that sandstone. But we're able to use those to analyze kind of how the mineralogy was changing, how the lake was changing through time. So here's a plot that just shows kind of, as we're climbing up, these are pie charts that represent like the basic mineralogy in each of these samples. And there's a lot on here. But kind of the grays and things are mafic igneous minerals that are just transported in. The greens are phyllosilicates, clays. And so we saw a lot of clays at the base and clays up here. The other one I want to point out is red is hematite and black is magnetite. So in general, a lot of the system looks still like that system we saw at the base, where we had a lot of phyllosilicates, a neutral kind of lake. One of the transitions we are seeing is between magnetite and hematite in different intervals. I think one of the better explanations that has been put forward to explain that is a redox stratified lake, where potentially the upper layer of the lake is oxidized and lower parts of the lake are reduced. And so you have kind of a transition depending on where we're driving through in the lake sediments, whether they're proximal or distal. We did see this one patch of particularly interesting. These 3 are actually pretty close to each other. The blue is crystalline silica. And so on Mars, we're really looking at a basaltic planet. And it's actually very rare to find any trace of silica. It's one of the things that's more different from Earth. And so this one patch that's about 50% silica, and in fact a big portion of that was tritomite, which is a high temperature, low pressure phase of silica that's usually associated with rhyolitic volcanism, was particularly interesting. And this is one of those kind of caveats to our understanding of that igneous system, or the petrologic system, is that we do have a lot of what appears to be igneous tritomite, and we had that one patch in the sandstone of what appears to be a lot of igneous sanidine. And so there are some kind of interesting things that we need to tease out about how the igneous rocks were evolving. And probably this is like the very late stage of magma evolution, and then you've just sampled it into the lake. But this is one of the kind of outstanding questions that we're working on. The big picture, though, here is to say that for a long time this lake existed and was habitable. Unfortunately, our drill broke, and so we haven't been able to obtain a sample for the last year and a half. But last 2 weeks ago, we tried again. The engineers at JPL are really good at kind of MacGyvering around problems on Mars. It was unfortunately, the first attempt was not successful, but we're really hoping to get a drill sample again really soon. The basic premise was that the drill extension feed broke. We finally managed to get the drill extended, but then it has no stabilizers, and we're not able to drill out and in. So instead we got it extended. We can drill into the surface and try to collect the sample like in the drill bit itself, and then rotate the drill bit backwards over our instruments to collect the sample. And just to this last week, it was unfortunately not quite deep enough to collect any sample, but we're really hoping that this works again. Just want to show a couple other features in that mudstone. These are some interesting diagenetic fractures that came in late. They probably represent overpressured water, so it's telling us something about the burial history of these sediments. And there are multiple layers of fracture fills in here. Calcium sulfate ones are bright white. Those are all forms of calcium sulfate. Gypsum anhydrite and basanite tend to be rolled into one around here. And then there's some darker fracture fills, which have variable kind of compositions throughout this that we're still trying to untangle. This is just to highlight something that we have to deal with sometimes that you might not have ever dealt with on Mars. These are calcium sulfate, so these are basically gypsum plates that are erosion resistant, and therefore making interpretation of bedding more difficult. You've probably never run into erosion-resistant gypsum before. When we saw this from a distance, we were excited about the cross-stratification, but it turns out that it's actually fracture fills of gypsum that stand out from a distance, when in reality the bedding is still our regular, steady, laminated mudstone, kind of highlighted in blue lines, whereas the calcium sulfate is in the yellow lines. So when you only have wind erosion and you don't have any rain, there are just a few things that are slightly different. This is our traverse at this point. Again, we haven't been able to drill for the last little while, so we're really hoping to at the top of our ridge unit. We're on this hematite ridge. It was called the hematite ridge because of what we saw from orbital spectroscopy. What we've learned is that the orbital spectroscopy was biased by dust cover, so there is not in fact more iron here. There may be more crystalline hematite at larger scales, but we're still working through the mineralogy. We're hoping to get the mineralogy soon. This is what it looks like from the ground, laminated mudstone. And there's ongoing debate about whether some of these are redox fronts or dust cover that sort of is oddly patchy to show what we're looking at right now. This is actually very, very literally what we are looking at right now. So this is our current location on Mars. These pictures came down this last week. These are the most recent color images we have. So we're sitting on that hematite ridge unit, looking down. So down here is the highest intensity clay ridge signal from orbit. And then as we get up here, we're getting into the sulfate unit. And so some of the base of this, where you see the really light tone deposits, are our transitional layer. And we're headed towards that as soon as we really hope to get this drill sample to work. on the ridge before we leave this unit, so we can figure out why it's a ridge and why it had that hematite signal from orbit. So just to say, there's still more to do after that. This is where we are now. We probably will not make it all the way up to the M-conformity, but there are a bunch of exciting units just ahead, and we're really looking forward to getting one real constraint or one example of that clay to sulfate transition and trying to understand the environmental significance of that, since we really do see that type of transition all around Mars. And so thanks for your attention.